just before we start on Fieldbus systems, we're just want to get a perspective of where they all fit into the scheme of things. And now you'll see on this chart here, we've got, if we start on the bottom left, sorry, bottom right hand side, I'll get the, basically pick up a pen I can point with. There we go, purple one that'll be. Okay, so what we've got here down at this end here, you'll see we have which are basically sensor bus systems, as you can see up the highlight at the top here. These are called sensor bus, and Fieldbus essentially means it's communication for field devices, and it was hoped originally when they set these up that we would have a one-size-fits-all digital replacement for 420 milliamp, and that simply is too complex and isn't going to happen. And so we've ended up with these ranges of devices from sensor bus, device bus, control bus, and field bus. And so under the sensor bus systems, we have essentially bit-based I/O. So things like here, which are, you can see some of the applications down here: switches, motor starters, push buttons, and sensors. And so we've got pretty standard offerings here, things like Seraplex, Sensorplex, we've got ASI and Interbus S, these ones here, which are essentially bit-based systems designed to be very fast, purely digital inputs. And then we move on to the next field, ones we're covering today, is DeviceNet. And so DeviceNet is one of the device bus systems, which is now designed to operate, and you can see DeviceNet actually runs right across up to smart devices. You can see on that vertical scale, and from block I/O. And so it's sending, these ones are sending messages that are of multi-byte messages instead of bits, and so that covers things like pressure sensors, barcode readers, motion controllers, all sorts of things where you're carrying multi-byte messages. Okay, so SDS, Smart Distributed Systems from Honeywell and DeviceNet. And then we move on to Profibus, and Profibus DP is designed for high-speed digital operations, and it can cover from bits up to bytes. And then we move through the control bus scenarios there. You've got ControlNet, Profibus FMS, and then Modbus Plus, Data Highway Plus, etc. And then finally on the top right-hand side, sorry, top left-hand side, we have what are called the Fieldbus systems here. And we'll be looking at these later on. We have Profibus PA and World FIP, Foundation Fieldbus. These are really aimed more at the plant applications, particularly for sensors and power feeding sensors and actuators devices across a pair of wires, and very often in a process environment where we're talking about having intrinsic safe issues, and we're bus powering the devices across those. And so they go to more complex systems. So the complexity is increasing as we go from right to left, and there are various variations to that. But that just gives you an overview of what the different field communication networks look like. They're essentially local area networks designed for operating in a noisy environment of a plant, and covering things from power feeding of instruments through to quite complex messaging systems. Okay, so let's move on to the next slide. And so on that slide, the different buses have different strengths and limitations. And as I say, it depends on all of these parameters. What's the support for the host system? area classifications and distance limitations depending on areas of intrinsic safety, equipment cost, the signal mix with analog or digitals, facility history, process needs, speed of response, and availability of devices to meet the required measurements and control. Okay, so we've got those things there. So, okay, and often with these, the best choice of which bus to use is often a combination. We can have different processes, different parts of the operation, different end users, and so there's a trade-off here of more complex systems with having more buses, or having one more complex bus for everything. So, okay, so that was just a quick overview of some of the buses, and there are a whole lot more than I've just listed out there for you. But those are some of the main ones that we're covering on the course. And of course, in the final module, we're looking at Ethernet-based high-speed communication, and we're looking at essentially the Ethernet versions of, in fact, DeviceNet, Profibus, and Foundation Fieldbus, and many others. Okay, so DeviceNet is built around the Controller Area Network, or CAN. So we have the CAN bus systems. There's Open CAN bus as an alternative, in fact, to DeviceNet, and CAN is used by SDS, Smart Distributed Systems. And the CAN network was developed for the automotive industry. Most modern motor vehicles have multiple buses in them, and particularly used for electronic ignition and the fuel management systems, but there's a whole lot of other applications for CAN bus as well. And what's special about CAN bus is it was developed to operate in an automotive environment, and it doesn't have a master. It doesn't use token passing. It uses what's called CSMA-CA, Carrier Sense Multiple Access with Collision Avoidance, as a way of sending the messages. And we'll elaborate on that just a little bit later on, because one of the things that this provides is it's very special in the way it works, because it always allows the highest priority device access to the bus. If two devices compete on the bus at the same time. And so, okay, very good. Okay, the CAN bus is used for lots of different applications, and it's a very widely used bus, say particularly for automotive systems. So the silicon devices for the CAN controllers are a standard off-the-shelf item which Bosch provides, and then other people have taken those and give the good additional features that we need. Okay, so DeviceNet operates as a bus, and it can be a 4-wire or a 2-wire bus, and typically it can provide one pair of wires for power and another pair for data, or you can independently power the devices. And because the speeds are not fantastically high, we're able to operate these with quite high speeds, but we are able to run drops off the bus. So you can see in this case that there's a drop length can be up to 6 meters, and it depends on the speed and the number of, we'll cover those a little bit later, the number of drops and the speed are a function of the particular type of cable and how fast you're going. So DeviceNet was developed by Alan Bradley. We'll come back to CAN bus a little bit later, and I'll explain how the actual access mechanism works. But first and foremost, we'll talk about the media and the wiring of devices. And so DeviceNet was developed by Alan Bradley using the CAN controllers, and then of course the Alan Bradley and Rockwell Automation have designed the software to interface that to higher level devices. And all the specifications are issued by the Open DeviceNet Vendor Association. I gave you their website earlier. So CAN is the controller area network, and it's an open standard. It's developed by Bosch as a serial daisy chain bus for fuel management and ignition systems in automotive applications. And of course, because these silicon chips have got a very high noise immunity, it's now widely used for an industrial fuel bus. So, but CAN itself does not specify the application layer nor all of the physical layer. And so it just covers essentially the data link layer and part of the physical layer. I'll cover that in a moment. Okay, so we covered that slide, so repetition. It doesn't use a bus master, but it actually has this CSMA-CA, collision avoidance, implemented as non-destructive bitwise arbitration. So, and now the thing about CAN is, you can see right down the bottom, it is not deterministic. Now when we say a system is deterministic, can anyone tell me what that actually means to you? Would someone like to tell me what deterministic means to you? Anyone? Okay. Can predict when a station will have access to the bus. Yes, that's a good explanation. Thank you. Yeah, it basically means that we can have a predictable performance. So it basically, but when we say something is deterministic, we need to say how, within what time this device must be able to access the bus. So we need to, just saying something's deterministic of itself is not enough. And you'll see when we start talking about in module part 4, the final session here, we start talking about some of the Ethernet systems with what we call hard real time. So we can have very short, very precise time constraints on our messages, and so we need to specify what the actual time requirement is. But deterministic in this case means that it's particularly, as I said, its particular benefit of using DeviceNet is it defers to the station with the highest priority. So, but it doesn't waste the particular time slot. So if two stations talk at the same time, the highest priority one gains access, and the lower priority ones drop off and try again later. And you can understand from a motor vehicle application, this is critical for example, with a fuel system, fuel injectors. We've filled the cylinder on our car with a fuel mixture. It would now be a very good time to actually fire the spark and actually use that fuel rather than do something else. So for that application, it's critical that we actually fire the spark at the correct time, and we lower priority applications defer. So that's the particular benefit of that. And so this is many other systems. When we talk like next week, talk about Profibus. Profibus is actually just a system which uses token passing and master slave, so it is deterministic, but that gives everyone a fair chance to operate, or it's up to the master, in fact, which slaves to operate at what times. But DeviceNet is different in that it's got this prioritizing process, so the highest priority station always gets access to the system. And the way this arbitration process takes place is that our physical layer we're using for our DeviceNet is essentially 485, and we're using, in this case, you'll see the terminating resistors are used to passively pull the bus line high, and we have transistors actively pulling the bus low. And so our bus has two states, which we can see here, which on the right-hand side here, where we have a recessive state, and this is high impedance, and that corresponds, remember, to our 485 system. Just quickly put up a blank page for a sec. So with 485, we'll just draw it up here. Our 485. No, heck with the expense. We'll go for a blank page. Here's our 485. 485. Okay, so what we have with 485 is we have a high and we have a low, and those are the two states. This is typically around +5, and this is 0, and then we had a high impedance condition. Well, for DeviceNet, the high impedance condition is the recessive state, which is equal to our logic 1. And so basically when we look at our bus, then we've got two signals here which look like this essentially. When we send the data bit, we have, this is the 1, and we've got CAN H and CAN L. And basically these typically going to be around, say, 2.5 volts here, 2.5. And then we have, so when we have a serious difference between that, we pull the CAN H line high and the CAN L line low, as we would with a, so we take our CAN H goes up to there and with CAN L goes down to the low. Then we generate the logic 0. Okay, so, and the 0 is the dominant state. So the 0 is dominant. And the point about that is, if the bus is in a recessive state, it can always be pulled dominant, but if it's in the dominant state, it cannot be pulled high, because we've got basically, it's only passively pulled by those resistors. So any of those transistors switched on, if we go back to the previous slide, any of these transistors switched on here will pull the bus low, but if they're all turned off, the bus will float high. So the bus is a high impedance state, and the dominant is the low impedance. Dominant, which equals 0, and recessive equals 1. So those are the conditions on our bus. All right. So when we start sending the bus arbitration process, it begins by the idle condition, which is recessive, and then we have, and you'll see in that with the format of the messages, we have a start bit. Move the mouse out of the way. Here, this is the start bit. So that's the start bit, which is equal to a 0. Okay, so, and then we go through our bits, and we go through the highest priority. This is well, bit 11 of our it's called our identifier, and then we start going bit by bit through those. And what happens is each device on the bus will now look at, he puts his data on the bus and looks to see what happens to the bus. So in this case, these stations 1, 2, and 3 all go low initially, So it's, and they watch the bus and they say yes, the bus has gone low. So that's good. Okay, then they all put a 1. So that was a 0. Then they put a 1 on the bus, and yes, they all see the bus go to a 1. So that's all happy. But then at this stage here, you'll see that these two guys have both put a 0 on the bus, and the bus goes low. But poor old 1 says, oh bother, I have been outvoted. And you can see here, he put a 1 on the bus, but he's been outvoted to the bus went low. So he then simply reverts to the recessive state and doesn't interfere with the communication anymore. He just simply drops out of the process. Meanwhile, stations 2 and 3 keep on going, and ultimately we find at this point down here, we'll change color. We'll see that in this bit here, 2 is dominant and 3 is recessive, and so simply 3 then stops and 2 carries on and sends his message. So this is where the highest priority stations actually transmit first, because the highest priority stations are the ones with the lowest addresses and have the more leading zeros, obviously, in their address, which is the identifier that we send out first. Okay, so that pretty much explains. This is basically another example of how this basically works. I think the words probably have made that reasonably clear. With that, you can see that they up to this point here, everyone has transmitted the same, and they've all put the appropriate bits on the bus, and then at this stage, node 1 is outvoted, and he stops transmitting, goes to the recessive state, and obviously he's then just pulls up and down in the normal sort of way. And then the next bit, in fact, node 2 stops in this case here, and node 3 carries on with control of the bus. Right, so yes, absolutely. It's very important that the application layer establishes what are the addresses. Yeah, before you set the addresses, and you'll find in a practical DeviceNet system that the lowest address is address 62 on the system, and that is used for all non-configured devices, and so that's the highest address, I should say, with all the ones. And the lowest addresses go to the PLC on the network. But yes, it's a matter of the allocations for these are set up, and for different priorities, and we'll come on to that a little bit later. You'll see where we have different classes of message, basically, to identify the different areas of priority.